Hi everyone, this is your struggling CS student here. So today let's solve another LeetCode problem. Let's take a look at today's problem. 1976, number of ways to arrive at destination. You are in a city that consists of n intersections numbered from 0 to n minus 1 with bidirectional roads between some intersections. The inputs are generated such that you can reach any intersection from any other intersection, okay, and that there is at most one road between any two intersections. You are given an integer n and a 2D array roads where road supply is equals to uv time means that there is a road between intersections u and v and takes time minutes to travel. You want to know in how many ways you can travel from intersection 0 to intersection n minus 1 in the shortest amount of time. Since the number of ways you can arrive at your destination in the shortest amount of time, return the number of ways that you can arrive at your destination in the shortest amount of time, and since the answer may be large, return it modulo 10 to the power 9 plus 7. Okay. N is only 200. Okay. There's at most one road connecting any two intersections. You can reach any intersection from any other intersection. Okay, what does that mean? You can reach any intersection. The inputs are generated such that you can reach any intersection from any other intersection, and there is at most one road between any two intersections. You can reach any intersection from any other intersection. Basically, yeah, it's always possible to reach from one node to another. Is that what you're trying to say? From 0 to n minus 1, okay, in the shortest amount of time. There are 4 ways to get there in 7 minutes. Oh, okay, I see what they mean now. Initially, my thoughts is to use the Dijkstra's algorithm because it's a single source shortest path problem. You want to know the shortest amount of time you can reach from intersection 0 to n minus 1. So in this case, the shortest amount of time it takes to go from intersection 0 to 6 is 7 minutes if we run Dijkstra's. Okay, fine. So 7, and they claim that there are 4 ways to get there in 7 minutes, and we want to know how many ways we can get there in the shortest amount of time. Ooh. Interesting. 0 to 6. Yeah, okay, there is almost one road between any two intersections. Basically, there are no parallel edges. There are no parallel edges. You can always reach any intersection from any other intersection. Okay, so basically connected components. The graph is always connected. The graph is always connected. So we have disconnected nodes. Like a brute force kind of way would be to find the shortest time it takes to reach n minus 1 from 0, then find all possible ways to reach n minus 1 in the shortest time t, right? Find the shortest time t it takes to reach n minus 1 from 0, then find all the possible ways to reach n minus 1 in the shortest time t. And then here, 2, 3, that's 8, so we can. So it's 1, 2, 3, 4. Okay. There's only one way to go from intersection to it, so it takes 10 minutes. Road dot length is always okay. As almost can reach, yeah. Honestly, not so sure about this one. feel like Dijkstra, but how? I'm thinking you can run like an initial Dijkstra from the source node to the destination node. Then afterwards, for all other nodes that is not equal to the source or the destination, you can find, um, actually that's not true. I want to say like you can find like the shortest path from all the other nodes that's not the source or the destination, and then you can find the time it takes to reach that particular node. It might work actually. So if let's say at this point, or rather at this node, what's the shortest path it can take to reach this node? It's 1, 2, and this. No, that means the shortest time it takes is this and this. Yes, okay. Then from here, you're only left with a budget of 2, right? You're only left with a budget of 2. How about here? Actually, can we think of them as this bidirectional thing? Can we just think of them as being directed? Like, there's no point in going back where we're always going downwards. In that case, since we're always going downwards, I'm not sure if we can think of it as a tree. If we're always going downwards, like in one direction, then there are no cycles. No, it's a deck, okay? It's a deck. And there are no cycles, I think. Shit, I'm stuck for this one. Time it takes for this guy to reach this guy. Time it takes for this guy to reach this guy. It'll be 2. This will also be 2. Here. I guess we can try the idea. Not entirely sure. So I'm thinking of like just using Dijkstra's first to go from the source node to the destination node. And then afterwards, we can process it kind of like a tree. So from the source node, we'll have like the initial budget, which is the shortest time that we have, right? Then we visit all of our children, right? So in this case, we'll visit like this is our root in a sense, or our source node. Then we visit 1, we visit 6, we visit 4, right? So our initial budget is 7. as long as we still have the budget to go forward, we can continue exploring down that path. So all the times that we can reach the destination node, then we will increment the answer by 1. That means we will traverse all the edges in linear time, I guess. And that would be, at most is, I'm not sure if that's like the best way of doing things, because you know what? Let's just try and see how it goes from there. So we'll run the thrust first. The distances is equals to infinity times n from map import infinity and distances of distances of 0 is equals to 0. Then we have a heap, which is the sort key will be the initial cumulative distance where we're starting at, which is actually 0, and the source node, which is also 0. Right. Then we also have something like this script, is equal to set, and while heap, the current distance, and the node is a heap of the heap. Okay, from heap Q and for heap up and heap push. And if the distances to the node is less than the current cumulative distance, what we have already explored thus far, right? If that is already lesser than what the cumulative distance is, then we don't have to traverse this edge anymore. Then we will continue. Otherwise, visited dot add node, and for neighbor in graph of node, and I realized that we actually have to build the graph first. If neighbor in C, continue, right? But we'll do that later. Then we will say something like the distance is equal to current distance plus weight. So we actually need to track the weight. Then we will say if the distance is less than the currently recorded distance to that node, then we will want to take this path. X equals to this, and hit push, heap of the neighbor and the distance. Okay, so then now let's build the graph. Graph is equals to, let's do this. Use dictionary comprehension for I in range of n, and for u, we w in rows. Say graph of u dot append vw. So we make it basically directed, because I don't think there's like any reason to revisit any of the nodes once we have visited that. There's no point in traversing back. Actually, let me check that the time is always positive. It should be, at least. Time is always positive. Okay, great. So lectures will fail if you have negative edges. So in this case, we don't. Okay, now we have like the shortest time will be distances of n minus 1. Once we have the shortest time, I'm thinking of like processing it kind of like a tree data structure. So we need to count all the ways we reach the destination node. So it's maybe something like count is equals to 0. That this would be a pre-order traversal of a node. If not node, no, rather if node is equal to n minus 1, then non-local count plus equals 1, and then return. Else, we will traverse from all of its children. So something like we also need to know the current rate actually, like the budget that we have. So we say something like, maybe say time remaining, right? Let's say time remaining. And we say for neighbor weight in graph of node, if the time remaining minus the current weight is greater than or equals to 0, we will try to take it, right? We'll try to take it. We'll do pre-order of the neighbor with the time remaining minus weight. Then we should do something like pre-order 0 of time remaining, which is the shortest time. And return count. Is that it? Scene. Oh, make this mistake again. Distances distance to, this is the neighbor actually. Really, I got that. Out of range. Zero, zero. For name graph of node. Continue. This equals just hit up. A. Current distance. Oh, what's going on? Index 7. How am I pushing index 7 inside there? Graph of view dot append VW. Oh, okay. I see the mistake. It should be like this. One positional argument, pre-order. Oh, what's it like that? Like this. Oh, it's wrong. Ha. Ah, dang it. Let's see what's the shortest time first. Shortest time. Shortest time is indeed 7, but we only count 2 ways to reach there. Why is that? Train node and time remaining. Then we're done. Else in graph of node, time remaining minus weight. Time remaining minus weight is greater than or equals to 0. Yeah, we can go down the path. The shortest time. Okay, let's take a look at our traversal. So we're starting from 0 with a budget of 7. We reach node 6 and yeah, one step, then we reach node 1. We reach node 1 with a budget of 5. Then we reach node 2 with a budget of 2. Then we reach node 5 with a budget of 1. Then from here, 5, 6. Oh wait, maybe I'm building the graph wrongly, you know? Maybe I'm building the graph wrongly. 5 and 6. Yeah, okay. I'm doing 6 and 5, 1. Oh shit, okay. I guess we have to be, it has to be bidirectional after all. Oh, okay. If it's bidirectional, it still works, right? But then this time we need to track the parent. We say parent, then we say the neighbor is equals to the parent, and we'll skip it. Otherwise, we'll do this, and parent is the current node. Okay, it's successful. However, I'm doubtful. Like, what's the time complexity for this? Count plus 1 mod. Mod mod is equal to 10 to the power 9 plus 7. What's the time complexity? This is O of V plus E log E. Pre-order, it looks linear to me, to be honest. I think it should be linear, right? Oh, it's always sketch, isn't it? Huh? To be honest, this is the only idea that I have anyway, so it's not like I have any other solutions. God dang it. Not sure if I can cache it, honestly. Will I visit the same one twice? Let's see, visit 1, 2, 3. Visit here. It's possible, actually. it's possible that, let's say we have another node here and we reach the same node here. Wait, but this cache doesn't really make any sense. Yeah. No, I'm not even returning anything. No. Yeah, but it's definitely possible. Like for example, if let's say we have another node here, I don't know, let's call this node x, right? So 0 to x with a cost of 4, right? 0 to x with a cost of 4. Oh, that's not good. No, 0 to x with a cost of 3, and then x to 3 with a cost of 1. Then here, it can go here, or it can go here. Oh no, then we have to explore both paths, right? Oh, well, okay, never mind. Anyway, I'm gonna YOLO submit. I feel like this is linear with respect to the number of edges. If let's say all of the edges can reach the destination node, and this would be linear, like O of E, right? Then the extra is just O of V, the time taken to initialize the initial data structures plus E log E here. And afterwards here, building the graph would be, this is O rows, right? So I feel like it should work, right? Oh, YOLO submit. Really? God dang it. I knew it. Looking like a TLE to me. Okay, but maybe the idea is there. Maybe the idea is there. But damn, okay. Let's see here. Really, if we cache it. If we manage to reach the node, we will return 1 bay, right? Return 1 way to reach there. We don't want to go backwards. Then we'll have something like answer is equals to 0. If we can, answer plus equals this, and then return answer. And actually, we should do something like answer is equal answer plus this, mod counts. Oh shit. Then we'll just return this. That's not sure honestly, but we can try. Ooh. Really? Yeah, we don't want to go backwards. But if we cache it, what is the parent can only ever take 1 value, that's fine. But time remaining, we need to know where we are currently. I mean, is it really better? Nope. Okay, it's a little bit faster, but not good enough. Not good enough. Let's see if we can remove some of the states. Let's see if we can remove some of the states. I feel like we definitely need to know what's the time remaining though. We also need to know where we currently is at. Turn on. Maybe we can do this. Oh. Not sure if we're double count in some instances. Oh, that's even worse. Actually, it's a little bit faster. Yeah, this is minimally what we need to know, right? Times up to 10 to the power 9. Yeah, okay, no wonder this is terrible. At our current node. At our current node. Thinking of a way to like shortcut it. I mean to say it's like, because we can reach the destination node can always reach the destination node from any other node, right? And it's like, as long as you reach a particular node with like a budget that is greater than something, well, what that means we still need to know the current budget and where we are currently at as well. Okay, YOLO submit again. I feel like this is not gonna work though, is it? Yeah, dang it. Yeah, it's because of that. It's because of this time remaining thing. Unless the question is like trying to bamboozle us and trying to say something like, oh, instead of counting all the ways to reach a particular node, we'll count all the ways that we can't reach a particular node, and then we will take all the possibilities, minus away all the like possibilities of reaching and not reaching a particular node, minus the number of ways that we can't reach a particular node, and then we derive our answer. That is so bullshit though. Like, because can't you go the other way around? You just have literally one way to reach the destination node, and then um, what you're counting instead would be symmetrical, because there's only one way to reach the destination node um, with within the shortest amount of time. Then you're just counting all the ways that you can't reach a particular node. Whereas if you just count all the ways that you can reach a particular node, then you only have one, something like that. Unless each node records the distance from that node to the destination node, and as long as we reach there with a given budget, let's say we reach here with a budget of 4, That means there will always be two paths, right? We just need to keep track of the distance. So we're building the answer like bottom up. Is that it? Really? I feel like that's not the way. So you come here. Explore all edges. N times n minus 1 divided by 2. N times n, yeah, let's use n squared only. What? Oh, why is it taking so long? Shit. N squared. Is it because I'm dealing with like very large numbers, that's why I'm timing out? That is possible, you know. Time of I. What does this time mean? Honestly, if that's the case, that would be so lame, to be honest. If the reason I'm timing out is because I'm dealing with large numbers, that would be kind of lame. Well, I don't think so. I don't think so, bro. Oh my days. Wow, this has got to be like some DP shit, man. Zero 046 01 01 256 01 356 0136. Or is there a 3 or 6? There are 4 ways to reach there. 0 to 6. 046. Oh, no, I'm trying. 0, 4, 6. Then you have 1, 2, 3, 5. 1, 2, 3, 5. So it's this to this. This is 5. This is this. This is 2. This is 7. This is 2. This is 3. This is also 3. This is 1, 1, 1, and 3. So what I'm thinking is we can like calculate the prefix sum in a sense. Oh, really? So this would be 7, right? This would be 2, this would be 5, this would also be 5, this would be 8, this would be 2, 5, 6, 7, 6. There is 1, 2, 3, 4. So, what does that help us? So this is like, when we change this to 5, that means here will be 7, here will be 8, and here there will be 2 costs, right? There will be 7, there will be 9, here, Really? Do we just eliminate impossible paths? Eliminate impossible paths. So we create like a new graph. I mean, we can try. Okay, so we still need a rank extras. And then in this case, we'll try to build a new graph. Pre-order is also fine. This is fine. Original graph. Then we'll create an edge. Really? There's no fucking way. Parent. Cannot unpack. Oh shit. Instant. Holy shit. Wait, this is what? Ah, that is. Looks weird though. Time remaining. It looks weird actually. Well, let's take a look. Here, 0, 6, 1, 4, then 1. Wait, what? Yeah, oh my god, this is very wrong. Oh, what the hell? I didn't do the pre-order part. Okay, time remaining. Just wait. Yeah, okay. If this was instant, then yeah, but I don't think so. Looking bleak. It is looking bleak. Make it just like this. Okay, I think it's over. It's actually just your. There's no way. Or at least, like, maybe there's some DP shit that I don't know, but yeah. You can explore down to 6, down to 1, 4, down to 1, and then down to 3 and 2, and down to 5 and then 6, right? Okay, that's not good. Okay, let's see what's up. Dijkstra's algorithm and graph theory. Huh? Floyd Warshall. DP. Interesting. 3D DP table. Wait, why does Dijkstra... Okay, how do you work? How does it work? Um, right. Okay, yeah. Yeah, okay, I get it. Path count keeps the number of ways to reach a particular node in the shortest time possible. Okay, path count is 0, is 1, since there's only one way to start at node 0. We reset its path count to the same number of ways as we could reach the previous node, since we have discovered a new optimal route. If we encounter another way to reach a node with the same, we do not reset, instead we just add. Since the number can be large, okay. Okay. Hmm, okay. Nice, okay. Okay, let's see. So it's just straight up Dextras, but this is Python. Build the graph, use Dextra, but we count the number of ways to reach the node in the shortest time. Well, mean heap. Okay. If this is shorter, you update this, then you say path count of the neighbor is number of ways to reach this particular node. As we found another way with the same shortest time, then we add it. Oh, okay. Interesting. I guess the key idea is this one. This one. Yeah, this is the key idea. Hmm. Yeah, okay, honestly, yeah, that's it for me for today. Yeah, I got bit by a problem, but it is what it is. Thanks for watching, guys.